At this time, Roy is the Vice President of the Central Appalachian Astronomy Club. Roy?
Thank you, sir. Yeah, just a little short note there. I contacted Mr. Naeye here last year, probably around October, November. At that time, he actually had to clear his schedule. He had to rearrange some things to come see us this year. And talked to him several times in the past. I was just made aware of his bio by the time we got it to put on our program. So it's pretty impressive. He's got his degree from science journalism from Boston University. He's worked for both astronomy and sky and telescope. So, like I said, I just want to introduce Mr. Robert Naeye, Editor-in-Chief of Sky and Telescope magazine. Thank you.
And I want to also thank Roy for pronouncing my last name correctly.
We learned how to spell it just a couple weeks ago.
That's right, yeah. If you want to know, it's a Flemish, and it's pronounced Noia, like paranoia.
Do you want some mic?
Sure, that'd be great. Yep. Can everybody hear me okay now?
Yes.
Okay, great. Okay. So as I think you know from the program, my topic tonight will be on amateur exoplanet discoveries. And before I get started, I want to first of all thank Roy for inviting me. I really appreciate it. I've had a great time here the last couple days. I want to thank all the people who organized the Green Bank StarQuest. Let's all give them a hand. Having previously worked at the Astronomical Society of the Pacific, in which we, every year organize an annual meeting, I know how much work goes into planning an event like this, and I know that Roy and his colleagues put a lot of time and effort so we can all have a good time. Although I guess we have to blame them a little bit for not giving us better weather. They should have planned that better. And I also want to thank the NRAO for, that's really generous of them to give us the run of their facilities. And from what I've seen, they've been very generous in letting us use their facilities and giving us tours and all that. So I really appreciate that. This is my second time to Green Bank. I might actually be here just a few months from now. I'm also speaking in September at the Almost Heaven Star Party, which is held very near here on Spruce Knob. So I might actually be back here at Green Bank in just a few months. And I just want to also thank all of you for coming, and I hope you're still having a great time despite the disappointing skies. Okay, so my talk tonight, of course, is about amateur science. And I think a lot of you know this, that if you go back even more decades, even more than 100 years, amateur astronomers have made a very impressive contribution to science. And in fact, that's one reason I think I'm interested in astronomy, in maybe contrast to other sciences, because it's really an area that for a very long period of time, amateurs have been able to play a significant role. For example, it's hard to think of like amateur, microbiologists. I certainly wouldn't want to have surgery done by like an amateur heart surgeon. Whereas on the other hand, I put a lot of trust in amateur scientists who do astronomy, and so do the professionals, as I'll make clear tonight. So over here, I kind of just list some areas where over the decades, amateurs have made very significant contributions to science. For example, monitoring variable stars, eclipsing binaries, discovering and characterizing novae and supernovae, discovering and tracking asteroids and comets, etc., etc. But despite these very impressive accomplishments, very few astronomers, like let's say I was giving this talk 20 years ago and saying that amateurs someday are going to play an important role in discovering and studying planets around other stars. This is what you guys would have said to me. So I think I'll make the case tonight, that they actually have. So let's just step back for a moment and consider where we were in mid-1995, and then look at how far we've come in just 18 years. In mid-1995, astronomers, and you can see right here, did not know of a single planet orbiting a normal star outside the solar system. Now, at that point, there were 3 exoplanets known orbiting a pulsar, but there were none known orbiting a star similar to the Sun. Now, I checked the web this morning, and I didn't use my airport. I did it with my Ethernet cable because I didn't want to interfere with the observations here at Green Bank. But I checked the website, exoplanets.eu. That's the Extrasolar Encyclopedia. And according to them, there are 910 known planets outside the solar system. So let's just say we'll include Pluto. That means we now know of 100 times more planets outside the solar system than inside the solar system. And I don't know if people can read at the bottom, the Kepler Space Telescope has discovered about 30,500 very good candidate exoplanets. And most of those are real planets, probably well over 90, and maybe as many as 95% of those candidates are real. So in other words, we probably actually know right now more than 4,000 planets outside the solar system, which, you know, considering that progress in just 18 years, I would say that's mind-boggling. Now, exoplanets are important to both scientists and the public, really for 2 reasons. The first one is by studying other systems, we learn about how planetary systems form and evolve. And I think, of course, the really big question is by learning about planets around other stars, we start to gain a better understanding for how common is life in the universe. You know, as far as we know, life is a phenomenon that we associate with planets. So the more planets there are out there in our galaxy, the better, the chances for extraterrestrial life. I should mention our latest issue, the one that subscribers should have already received and that's on the newsstand right now, is the cover story is by a very brilliant exoplanet researcher at MIT named Sarah Seeger, and it sort of is a really comprehensive summary of what we know right now about exoplanets. One very conservative statement that we can make is based on the frequency of planets that have been discovered, we can say there are probably at least 100 billion planets in the Milky Way galaxy. At least 100 billion. At least about 1 per star. Okay, so not only now do we know about 900 plus exoplanets, we're actually starting to learn about some of the characteristics, the density, the composition, some of their weather patterns, what's going on in the upper atmospheres of these worlds. And as I'll show, I'm not nuts when I say that amateurs have been playing a key role. And I know for an absolute fact by talking to people like Sarah Seeger, Jeff Marcy, and other leading exoplanet researchers that they very much appreciate and have a very, very high level of respect for the amateurs who are doing this work. Okay, so I'm going to go back for a minute. And probably a lot of you know this already, but most of the planets that have been discovered to date, and certainly the first few dozen found around normal stars, were discovered by using what's known as the radial velocity method, or also known as the Wobble Method. Let me just go back and restart this movie. You'll notice the planet here going around the star, but the star responds to the gravitational energy of the planet. So the star is also tracing a little wobble. And when that wobble happens, you can see the diagram at the upper left. When the star is then moving toward Earth, its spectral lines are shifted to the blue. When the star is moving away, the spectral lines are shifted toward the red. So by looking at the spectrum of other stars, we can deduce the presence of orbiting planetary companions. The very first planet discovered using this method, and of course the first star found around a solar-type star, was in mid-1995 around a star actually very similar to the Sun, a little hotter and more evolved than the Sun, called 51 Pegasi b. I'm sure here from Green Bank on a clear night it would be visible to the naked eye. I can't remember, I think it's a 4th or 5th magnitude star. And the planet was discovered by the two astronomers at the upper left, Michel Mayor and Didier Queloz of the Geneva Observatory in Switzerland. For some of you who remember, this was a watershed event in the history of astronomy, and it did make news worldwide. The one bizarre thing, though, there's the radial velocity plot on the lower left showing the motion of the star going away and toward Earth, is that the planet was completely unexpected. It's a planet about, maybe half to 1 Jupiter mass in an orbit that's only 4 days. So it was the prototype of a class of planets that I'll be talking a lot about tonight called a hot Jupiter. It's like taking Jupiter and moving it so it's just, almost just barely beyond, the star's chromosphere, whipping around the star in just a few days with its upper atmosphere heated to thousands of degrees. Certainly not a planet that was expected. Okay, the next 2 planets then were found by an American team, Paul Butler on the left and Jeff Marcy on the right, who were then working out at the University of California. Jeff Marcy, by the way, is on the Kepler team now. Marcy has discovered more exoplanets than any human being or more planets total than any human being in history. And not only that, he's never had to retract any of his announced planets. He's a very, very careful scientist, so in essence his batting average is 1,000. Here's just showing a radial velocity plot of one of their first 2 planets called 47 Ursae Majoris b. This is a world about maybe 2 or 3 times the mass of Jupiter. You can see in the middle there, the distance from the star is 2.1 AU. That would essentially put it, in the asteroid belt were it orbiting the sun. Their other planet was kind of a weirdo. You can see, for those of you in the front at least, you can see at the lower right, this is a planet with a very skewed plot on the left, and that's due to a very highly eccentric orbit or elongated orbit. This is a planet with about 7 times the mass of Jupiter that orbits, kind of between Mercury and Venus if it were in our solar system, but in a highly elongated orbit. This is a planet that probably was the survivor of a system that started off with more planets, and they started to perturb each other. Some of the planets got slingshotted out into the frozen depths of intergalactic space, leaving behind this very, very massive planet. Some might even characterize this object as more like a brown dwarf than a planet. The distinction is still a little bit fuzzy. So by the late 1990s, astronomers had discovered dozens of exoplanets. We had the 3 pulsar planets, and then several dozen of these planets discovered by radial velocity. But at that point, astronomers are eager to take the next step, starting to really understand the nature of these worlds, not just their mass and orbit, but what are they like, their atmospheres, their compositions, what are their densities, etc. And then, of course, another big goal, especially for those interested in extraterrestrial life, is finding smaller planets, the ones the size of Earth, that as far as we know, based on our one known example of life, have the best prospects for harboring life as we know it. So another method for finding planets is using what are called transits. Let me play that back. And you'll notice as the planet crosses across the star, you'll notice, look at the light curve at the bottom, you see a very brief but very discernible drop in the star's light. This is very similar in concept to the observations of transits of Venus and Mars. Of course, we just had a Venus transit just about a year ago. I know some of the people here in the audience saw it. How many people saw either the 2004 or the 2012 transit of Venus? That's great. I figured it would be a pretty high percentage. And if memory serves me correctly, there's a Mercury transit coming up in 2016, and if I'm remembering properly, North America is very well positioned to see it. So for those of you who missed the Venus transit, you can see another planet transit in just about 2 years or 3 years. So late 1999 was the big breakthrough, because that year there were two different teams, both professionals. One was a team led by Dave Charbonneau, who works at the Harvard-Smithsonian Center for Astrophysics. By the way, if you ever meet Dave, you'll immediately know it. He's about like 6'8" tall. He's actually originally from Canada, but he's a great guy, but he's very, very tall. So when he walks into a room, you immediately notice his presence. And he was working with Tim Brown, who works at the National Center for Atmospheric Research in Colorado. Then independently, an astronomer named Greg Henry at Tennessee State University, what they detected was that a known planet, this was a planet that had been discovered by Marcy and Butler in the radial velocity work, that was known to orbit the star HD 209458. They discovered that this planet, in fact, at the predicted time, passes in front of the star and blocks a little bit of the light. And so because it blocks some of the star's light, and we know the spectral type and type of the star, by measuring how much of the star's light is blocked, that tells you the radius of the planet. And because you know the mass from the radial velocity, and because you know the size from the transit, you can then calculate the density of the planet. And it turns out at the bottom here, I don't know if some of you can see it, but the density is 0.35 grams per cubic centimeter. Of course, water is 1 gram per cubic centimeter. So this is a very, very low density world. It's kind of like a puffed up Saturn or so. It's in between actually Saturn and Jupiter in mass, but its diameter is about 1.5 Jupiters in diameter. So it's a very, very puffed up planet, likely because of its very close proximity to the star. Its orbital period is only 3.5 days, which is pretty ridiculous, at least by solar system standards. Okay, this is where the amateurs enter the picture. Less than a year later, after this transit had been announced, a group of amateurs in Finland decided to see if they could detect the transit, because it's a big planet, it's fairly close to the star, and it's a relatively bright star. And you can see their light curve at the upper left that shows the brightness of the star over time. You can see that very pronounced dip. And this was actually a very easy detection. The group, by the way, you can see R2 Oksanen from the Naeye Observatory in Finland using a Meade telescope and an S-Big CCD camera. And it turned out, I mean, this was not a marginal detection. This was a very clear and obvious detection. And this, this sent the signal to the whole amateur community around the world that amateurs could now enter the exoplanet game. By about 2000, amateurs had access to good enough and affordable CCD cameras that they could monitor the brightness of stars to a precision of about 1%. And because a hot Jupiter causes a decrease in the star's brightness of maybe like 2, 3, or 4%, that's definitely good enough to do this type of measurement. There's no doubt at this time that amateurs could detect exoplanet transits. And of course, the technology got better and better. CCD cameras improved, the software got better, amateurs improved their technique. So right now, amateurs are currently achieving about 0.1% precision in their photometric. That's monitoring the brightness of a star over time. Because of this equipment, and that's easily good enough, to detect a lot of the known transiting exoplanets. And just to show you that you don't even need a big telescope, this is Tim Brown, who I mentioned earlier. Now he's a professional, but he actually discovered a transiting exoplanet with a 4-inch telescope. You can see his telescope at the upper left. This was a telescope based in the Canary Islands. This was a planet that was discovered by the transit and then confirmed by doing the radial velocity. Usually it's the other way around, but this one he discovered the transits. So how many of you in the audience have at least a telescope of 4 inches in aperture? I figured to be a pretty high percentage. So the key here is you don't even need a big telescope to do this. Now, just 8 days after Brown announced this planet publicly, a Belgian amateur astronomer, Tony van Munster, who's been very active in this research, he decided to try to detect it from his home observatory. He uses a 14-inch celestron, and you can see his light curve at the upper right, and he had no problem detecting it. In fact, his photometric data is so good that the professionals used his data to help pin down the diameter of the planet, which of course then you can calculate the density. Another key thing about these transiting planets, this is something that amateurs can't do, at least not yet, but it shows you the importance of transiting planets, is during the transit, the sum of the star's light is passing through the upper atmosphere of the planet, inducing absorption lines. Some of the molecules and elements in the upper atmosphere of the planet are going to absorb some of the light from the star and leave an imprint. Now, when you look at the star when the planet is not in transit, those lines go away. So you can really make a very clear-cut detection with this. Especially right now, Hubble is doing this. Certainly when the James Webb Space Telescope launches, that's going to be a very high priority, because you could use this type of observation to find evidence of life on another planet if you found, let's say, things like ozone, carbon dioxide, and water vapor on an exoplanet. But this has now been done on several dozen planets where they have found things like sodium, CO2, carbon monoxide, and methane have been detected in the atmospheres of extrasolar planets that transit their stars. So you can see how valuable these transiting exoplanets are and why they're so cherished by professional astronomers. Another thing you can do, this is an experiment that's been done with Spitzer, is if the planet transits, in other words, it crosses the star from Earth's line of sight, there's a very high probability that on the opposite side of the orbit, it will pass behind the star, and from Earth's perspective, the planet disappears. So you can look at the star when the planet is in view, and when it's not in view. You subtract the two results. If you do this in infrared, you can see the light curves of these stars at the bottom, and that tells you the temperature of the planet's upper atmosphere. So this has also been done on several known planets, which is another really important measurement, because you can start to learn about the weather patterns in the upper atmospheres of these exoplanets. Another one that was discovered, this was a really major discovery in June 2005, was a planet known as HD 149026b, was discovered to transit its star. And what was really exciting about this one is it's a very small planet. Now, even before, what happened is Jeff Marcy's group discovered the transit, but before they announced it publicly, they communicated to some amateur astronomers to try to repeat their observation. One of these amateurs was Ron Bissinger, who lives in Pleasanton, California, near Berkeley and Oakland. And you can see his light curve here on the right. And he actually made this detection before this planet was even officially announced to the public. What's really impressive about Bissinger's observation is that this is a relatively small planet that causes only a 0.003 magnitude decrease in the star's brightness. So this shows that amateurs can do very, very sensitive, precise observations. I actually wrote an article about this for Sky and Tell, and when I interviewed Jeff Marcy, he said, "That is truly beautiful work Ron is doing, and it is contributing to the precision of the radius measurement for the planet." And this is a very strange planet, because when astronomers like Sarah Seeger model its interior based on what we now know about its mass and density, they find that this planet is comprised of about 1/2 to 2/3 heavy elements, things like carbon, silicon, iron, not hydrogen and helium. And so the calculated mass of the core of this planet is about 70 Earth masses of heavy elements. So this planet is wildly different from anything we have in the solar system, very different from a gas giant like Jupiter, Saturn, or even Uranus and Neptune. So this was a real signal that there's a lot of weird planets out there that we don't have any analogs in the solar system. And it told astronomers, hey, wait a minute, these planets orbiting other stars are not just like similar to the worlds in our solar system, that the planetary zoo in the galaxy is unbelievably diverse. Okay, now the first time that amateurs made a major contribution in discovering a transiting exoplanet was just about a year later in 2006, when several different amateurs, including Ron Bissinger, but also Bruce Gary in Arizona, who's been also very active in this type of work, and at the bottom left, Steve Howell in Maine, helped actually discover a transiting exoplanet working with a professional astronomer, Peter McCullough, at the Space Telescope Science Institute in Baltimore. Now, two other professionals who were very quick to recognize this very powerful potential contribution for amateurs were Greg Laughlin at UC Santa Cruz at the upper left and Tim Castellano at NASA Ames at the upper right. By the way, for those of you who subscribe to S&T, we had an article in the May issue about exoplanets and how they get in these strange, bizarre orbits. Greg wrote that feature article. He's actually a really, really good writer, which belies this notion that scientists can't write for the public. He proves emphatically that that is not true, because he's actually a very good writer. So what they did, I don't want to go through all these bullet points here, but they organized a global network of both professionals and amateurs to look for planets that were already known to exist from the radial velocity studies, but they calculated when they should transit their stars if they were in the right line of sight, and then get amateurs around the world to look at these stars to see, in fact, if they would transit. Now, most professionals would not do this work because even if a planet is very close to its star, it might only have a 1 to 10% probability of being in the right alignment where it will transit. Now, if you're a professional and you go to your observatory director and say, I want to do this measurement, but I only have a couple, 2 or 3% of detecting anything interesting, you're most likely going to be saying your proposal's rejected. But what if you're an amateur astronomer and you can do whatever you want with your telescope in your backyard, and you know that if, let's say you do about 10 or 20 stars, sooner or later, even if your probability is fairly low, you do this enough times, you're guaranteed. It's just like if you're playing Russian roulette. If you play it enough times, you're going to fire the bullet. But if even if you have low odds, this is not like 0.0001%. This is 1 to 10%. So you do 10 or 20 stars, you're going to make a discovery. It's inevitable. So this was the strategy that Greg and Tim developed, and they had very little problem getting amateurs to cooperate and join this organization. So very shortly after they organized the campaign, they hit the jackpot. And as I said, this wasn't like where they got lucky. They had the right experiment, the right strategy. It was guaranteed that sooner or later they were going to discover that a known planet was transiting its star. It was a guarantee. It was a surefire thing that they were going to find one, or more than one. So the first one they found was a planet orbiting the star HD 17156. And this is one where I really wish these stars would have more, poetic names. I get, especially trying to remember all these Henry Draper catalog numbers gets a little frustrating. So this was partially discovered by amateurs, and what made this one really significant is you can see the orbit of the planet. This planet had a 21.2-day orbit, and also notice it's an elongated orbit. Now that sounds really short, 21.2 days, But up until then, the previous record holder for the longest orbital period for a transiting exoplanet was 5.66 days. So this was a really different kind of planet than all of the other transiting exoplanets that were known up to that time. So here we see the discovery light curves by several different astronomers. The top one is by an astronomer in Italy who got clouded out. The one in the middle is from a professional astronomer in the Canary Islands. Then you can see the third and fourth ones down are from two amateurs in Italy who clearly caught the beginning phases of the transit. In fact, Lopresti got most of it. Now, the reason they didn't get the entire transit, and that's actually the weather map at the lower left, there was clouds that rolled in and covered up Italy. Otherwise, Lopresti and Gaspari would have observed the entire transit. But they got enough of it to really show beyond any doubt that it was real. Then the guy in the Canary Islands, he got the beginning and end, but not the middle. And then you can see Ron Bissinger. Unfortunately for Ron, he easily could have detected it. Unfortunately, the star had not yet risen at his location in California when the transit ended. But clearly, this was a very clear and not a marginal detection. So here we see the two Italian amateurs, Claudio Lopresti and Daniel Gaspari, who made this discovery. And at the bottom right, when I interviewed Sarah Seeger about this, this was her quote: "This is a fantastic historic discovery. First, it enables us to study a planet very different from the normal hot Jupiters. This discovery is also historic because amateurs help detect the transits." So this is actually artwork done by Greg Laughlin of what the planet might look like. Because it has such an eccentric or elongated orbit, it experiences a 26-fold variation in the amount of energy it receives from its star during the course of its orbit. So this would not be a very pleasant planet to live on. The temperatures would swing in the upper atmosphere on the day side between 800 and 2400 degrees Fahrenheit, which should drive very high-speed winds and very complex meteorology. Okay, then just a couple years later, more Italian amateurs helped smash that record by helping to discover a transiting planet with a 111-day orbital period. And for those of you who can see the movie on the left, you can see the planet spends most of its time relatively far from the star, and then when it comes in, it whips around really, really fast. These are the light curves of the Italians on the right, and they got the egress, the end of the light curve, or the end of the transit very, very convincingly. Okay, then 111 days after that transit was discovered, astronomers knew it was going to transit again because it has a 111-day period. So a professional astronomer at MIT named Joshua Wynn lined up a bunch of professional and amateur astronomers to observe the next transit. And this led to a very major discovery. And the most important data of this transit in June 2009 came from this astronomer in this photo, Don Starkey of Auburn, Indiana. And as Joshua told me when I interviewed him, he said Don was in the right place at the right time under clear skies and expertly observed the ingress. That's the beginning of the transit. His data proved to be the most valuable of any photometric data that we collected, amateur or professional. Now this is the work, a composite light curve that Joshua Wynn put together. The data points from Don Starkey are the green points in this composite light curve, putting data together from a number of different amateurs and professionals, a composite of both the February and June transits. Now, what was very interesting, as the star is rotating, and as the planet is transiting, and you can also take the spectrum, and by seeing how much of the red-shifted and blue-shifted light is being blocked by the planet as it transits, you can then, and this is a technique known as the Rossiter-Mclaughlin effect that's been used to study eclipsing binary stars. Joshua Wynne was able to show, and this is really bizarre because there's nothing like this in the solar system, that this planet, which remember has a very elongated orbit, is tipped. Its orbit is tipped 40 degrees to the star's equator, its rotation axis, which is, there's nothing like that in the solar system. You know, all the planets in the solar system are, you know, within a few degrees of the sun's equator. So this is unlike anything in the solar system, and this is almost certainly due to complex gravitational interactions between the planet, its host star, and we know that this star has a more distant binary companion. So this showed that planets can kind of get yanked out of their formation orbits and end up getting parked in orbits that are either very inclined, or since this discovery, they've discovered that some of the transiting planets go around their stars in the opposite direction in which they rotate, which is really bizarre. So the current scorecard is, and I checked this morning, is we have 312 known transiting exoplanets, many of them discovered in the last few years from NASA's Kepler Space Telescope. Many of them have been detected by amateurs, and as Greg Laughlin said, until recently, that's the Kepler ones, and because those are generally very faint stars, all of the scientifically interesting ones have been detected by amateurs. So this transitsearch.org is continuing its project, and once again, they're looking at planets in eccentric, longer period orbits that professionals rarely attempt to observe because of the low probability of transits. So the next, as I get close to the end of my talk, I want to now shift gears to an entirely different method for detecting exoplanets. This method has detected several dozen planets. It hasn't been as rich as radial velocity or transit, but it's still in third place for most planets discovered. And this is a technique that takes advantage of a quirk in Einstein's general theory of relativity that's known as gravitational lensing. Interesting, when Einstein realized this in his equations for relativity, he predicted that this effect exists in nature, but we would never actually have the ability to see it in real life. Well, not only have professionals seen it, as I'll show you, even amateurs can now detect, amateur astronomers can detect this effect. So Einstein was brilliant in one aspect, but he was very wrong in predicting, he was very, back then, they just didn't envision the kind of technological improvements that would occur over the next 100 years. So what happens is if you have a background star, let's say orbiting the center of the galaxy in the bulge, like 20,000 light years away, and then you take a star that's, let's say, 10,000 light years away, and as it's drifting across, its proper motion, it drifts right in front of the background star. Its gravity will take some of the light rays from the background star, redirect them to light rays that would otherwise not hit Earth, redirect them so that they will hit Earth, leading, you can see it at the upper right, leading to a very beautifully symmetrical increase and then decrease in the light of the background star over the course of maybe several weeks to several months. Now, if the star has a planet around it, that planet, near the peak intensity, when the alignment is perfect, the planet will disturb that perfect symmetry in a way I'll show you in just a minute. So a big step for amateurs was the direct participation in the discovery of a micro-lensing exoplanet. And once again, kind of an ungainly name. The OGLE stands for the Optical Gravitational Lensing Experiment. The year was 2005. They were looking toward the bulge of our galaxy, that's for the BLG, and it was the 71st micro-lensing event, except this one, it wasn't just a star, this was a star that had a planet. And there were two New Zealanders, two Kiwis, who played an essential role in this discovery, two amateurs, Grant Christie on the left and Jenny McCormick on the right. And one of the professionals on the team, Scott Gowdy, and I know I'm supposed to say the Ohio State University, told me in an interview the amateur data was essential to understand what was going on. And no doubt the best quote in my talk tonight comes from Jenny McCormick, and she said, "It just shows that you can be a mother, you can work full-time, and you can still go out there and find planets." So this is an artist rendition on the left of what this planet might look like. We really don't know, but we do know it's about 3 times the mass of Jupiter, and it orbits the star at about 3 AU. That would put it in the asteroid belt, and the star is about 15,000 light years from Earth. Now you can see the light curve here at the lower right. Now actually let me get out this laser. I wasn't allowed to use my own because it puts out a little radio signal. Now if there had not been a planet, you can see this is a blow up of this peak critical period where the event would have peaked. If the light curve would have followed this dotted line, but instead it went up, down, and then up again at that crucial moment. This is a period that was just literally over a day or two, and some of this New Zealand data was right in this critical period where you could see it deviating from prediction. And by the way it deviated, you can do calculations. Believe me, this is way beyond anything I could do. But from the way the light was deviated, that's how you get the mass and the approximate distance of the planet. Then, not very much later, in 2008, several amateurs, both Grant Christie, Jenny McCormick, an amateur in Italy named Franco Malia, another Kiwi, Tim Natush, I don't know if I'm pronouncing that right, they actually discovered a microlensing event that had 2 planets orbiting the lensing star. This one was really interesting because the planets are very much analogous to Jupiter and Saturn. They have masses of about 0.71 and 0.27 Jupiters, and they orbit at about 2.3 and 4.6 AU from a star that's about half the mass of the Sun. So they're a little bit smaller than Jupiter and Saturn. They orbit a little bit closer in, but they're orbiting a less massive star than the Sun. Then there was another Jupiter analog discovered in 2008 in which the most significant data was produced by Bertu Menard, an amateur in South Africa. You can see him here with his Meade telescope, and he uses an S-big CCD camera. And then there was another one, a sub-Saturn mass planet, that Bertu Menard also contributed a lot of data to the discovery. Now, when I interviewed Scott Gowdy at Ohio State about this, he said most of the data that led to the planet discovery was taken by Bertu Menard. The only difference between working with amateurs and professionals is that I don't have to pay the amateurs. I don't know how all of you amateurs I think you should take that as a sign of respect and not like using you as slave labor. There's been many other amateurs have contributed to help discover this planet, which was announced about a year ago, the OGLE BLG 2012 event. And this is interesting, a 0.11 Jupiter mass and a 0.6 Jupiter mass planet, so another double planet system. And these are pretty low mass planets. And this shows you the power of this microlensing technique. For the final part of my talk, then, I want to shift gears again. Now, let's say there's some of you in this audience, and you want to discover an extrasolar planet, but you don't want to learn how, you don't want to buy a CCD camera, you don't want to go through the hassle of learning how to do photometry and reducing your data. Well, it turns out you don't need anything other than a computer, an internet connection, and a little bit of enthusiasm. How many of you have all 3 of these things? A computer, an internet connection, and a little bit of enthusiasm. I have a feeling it's pretty much everybody in the room here. What you can do, and you can do this tonight, very simple to remember, planethunters.org, and you can sign up. You get a little tutorial where you look through Kepler data and you can start looking for transiting planets that were missed by the Kepler science team and their computers in the Kepler data. It's something that's not that hard to do. Now, I've got the latest update, and since this project got going in December 2010, about 250,000 citizen scientists all around the world have helped professionals analyze the light curves of the 160,000 stars in the Kepler data. One of the members of the team, Meg Schwam, she told me that there are 13 million analyzed light curves from the citizen scientists. This is a little too gender specific, but I hope you agree that's a pretty impressive number, 180 man-years. That's a lot of time. Now, what's really impressive is that Planet Hunter volunteers have now identified 20 candidate planets that the Kepler science team missed, and there's undoubtedly more to come. And as Deborah Fisher, who's at Yale University, told me, this is the first time that the public has used data from a NASA space mission to detect possible planets orbiting other stars. I think there's a 95% chance or greater that these are bona fide planets. So probably like 19 of those 20 planets are real planets and eventually will be confirmed. And not only do we have those candidates, there is one confirmed planet from the Planet Hunters team. This is an artist rendition here. A planet with it's about 6 times the diameter of Earth, so a little bit bigger than Uranus or Neptune, in a 20-day orbit around an eclipsing binary. So there's 2 stars going around each other. Now this planet goes around both stars. It's not orbiting one of the 2 stars. It's what's known as a circumbinary planet. It's only one of 7 known to exist. And we now know, and this is the artist's rendition, that it's actually a quadruple system where there's another binary star at a much greater distance from these other 2. So this is the only known 4-star system, a quadruple star system that has a planet, and this planet was discovered by citizen scientists who just had, looked at these light curves on their computers. So, I mean, this is a very, very significant scientific discovery, and once again, you don't even need a telescope to do this work. So there's going to be more of these discoveries to come in the future. So I want to conclude by giving you my fearless forecast for what is to come. Amateurs, especially in Europe, have been using these commercially available spectrographs, and they've actually made a number of detections using the radial velocity method of known extrasolar planets. This is a 3-Jupiter mass planet orbiting the star Tau Boötis. They've also detected 51 Pegasi. That was the one Mayor and K. Lowe detected in 1995. So the fact that they can detect them, they get lucky if they look at the right star with a fairly massive inner planet that hasn't been studied yet. They could discover a planet using this radial velocity technique. So that might happen sometime in the next few years. We're definitely going to get, with TransitSearch.org, more amateur detections of long-period exoplanets. There's going to be more microlensing discovery with amateur participation, including findings of very low-mass planets, even potentially down to the mass of Earth. And what's really amazing, and you can read our article in the July 2009 issue, if you look at a transit, if you start to see from one transit to the next, variations in both the timing and duration of these transits, that could be due to the gravitational perturbations of a moon orbiting the planet. So it is possible that the first detection of a moon orbiting a planet outside the solar system could be made by amateur astronomers. And of course, we're definitely going to get more planets from planethunters.org. So for further information, and I can put this slide up later for those of you who are interested, as I said, this is really the main one to go to. There's lots of good resources on the web. I just want to point out before I conclude, is we have a lot of articles about exoplanets in our latest special edition called Astronomy's 60 Greatest Mysteries. I actually picked up 3 copies yesterday on my way here at the Books A Million store in Martinsburg, West Virginia, right off Interstate 81. So it's definitely out there on newsstands. You can also get it through our website, and we have 1 copy available for the raffle tonight. And it has lots of great articles by some of the world's leading astronomers, including Jeff Marcy and Sarah Seeger. We've got an article from Britain's Astronomer Royal, Sir Martin Rees. We've got a couple articles from Greg Benford, who's not only an astrophysicist, but also a well-known science fiction writer. Our latest issue of S&T, as I mentioned a few minutes ago, the cover story is about the exoplanet revolution, about all the amazing things we've learned about planets orbiting other stars. So I just want to conclude with a thank you for your attention. My guess is the first question that you have, so I'll answer it before any of you even ask it, is where this photo was taken. And I have to admit, I'm a little bit embarrassed to admit this, but this was taken at the UFO Museum in Roswell, New Mexico. So I know we do want to get to the raffle, but I'm happy to take some questions.
Turn the light up a little. Help you see.
Okay, I see a question over here.
How'd you do your fingers so well?
Yeah, that's supposed to be the Vulcan. I can still do it. Maybe I've watched too many Star Trek episodes. I'm not really a Trekker, like I've never gone to a convention, but I did, I've watched. I haven't even seen the most recent movie, though, because I heard it wasn't very good. Is it good? It is good? Okay, should I go see it then? Okay. Okay. Let's see, question over here.
What is the cost of the gear to get going on something like this, the spectrograph or whatever? Obviously, you've got to have a camera on it.
Yeah, you need, you can do this with really small telescopes. If you want to go to fainter stars, you might want a scope of like 8 to 10 inches of aperture. You obviously need a good mount, and you need a good CCD camera. But the commercially available ones now from SBIG, Apogee, FLI, there's a whole bunch of companies out there that are making really, really good equipment. So let me think a minute here. I think we're talking probably, putting everything together, probably you could do this for less than $5,000. At least the transit, and even maybe the micro lensing too. The main obstacles, you have to really learn how to do the precise photometry. But once again, there are hundreds of amateurs around the world, or maybe even thousands now, who are doing this. Either exoplanets or variable star work, or for example, there's amateurs monitoring asteroids to measure their rotation rates and looking for binaries. There's a lot, like some of those websites too, really give very, believe me, how to do this would be the subject of an entire other talk. But you do need to have some fairly good technical skills, but they're technical skills that are well within the range of amateurs who are eager to participate. And amateurs are professionals like Scott Gowdy, Peter McCullough, and Greg Laughlin are going to be willing to spend, and they've done this, willing to spend time with amateurs helping to teach them how to do this kind of research. So if you're interested in trying to discover X-transiting or micro-lensing planets, there's a lot of help available out there. And once again, these professionals are eager to work with amateurs. It's not like a case like, well, I don't know if I really trust these people. They're like, we want your help and we're willing to help you along. Let's see, Howie?
Bob, how do you think the information that we've gained in the last 15 years or so about exoplanets it could be put together with like Drake's equation? How would...
And that's a great question, and Sarah Seeger addresses that in this article. what I said earlier is we now know that there are at least 100 billion planets orbiting stars. There's probably another 100 billion rogue planets that are cast adrift in interstellar space. So we know that planets are very common. We also know that smaller planets are more common than large planets. Now, all the planets discovered early on were large because they're heavy, they produce a radial velocity signature, and they block more of the star's light, so they're easier to detect by transits. But what Kepler has shown by monitoring 160,000 stars is Kepler is finding many more small planets than large planets. We also are now finding out that planets are very common in the habitable zones of stars. Okay, that there's no doubt. So I'm going to give you, I would say this is a extremely conservative estimate. Okay, there are at least 1 billion planets, roughly the size of Earth, a little bigger, a little smaller, or the size of Earth, orbiting within the habitable zones of stars that are potentially capable of supporting life.
So does that mean that people that don't believe that there's other intelligent life in the universe, that they're the crazy ones?
Well, and there's actually, in that special issue about the 60 Mysteries, there's a debate about that question between Seth Shostak, who's spoken here, I know, at this event, and another astronomer at UCLA named Ben Zuckerman, who I think makes a fairly compelling case that, technologically, because I'm not sure we're intelligent, considering some of the things we're doing, and that's the case he makes too. I think Ben makes a fairly compelling argument that intelligent life might be very rare, or technologically capable life. I'm going to give you my belief, but this is a belief. It's not just my gut feeling, because we haven't discovered life yet on any planet other than Earth. I think that our galaxy probably has at least 1 billion, probably many more than 1 billion, planets that at least have some kind of primitive life. But I would not think that necessarily translates to a lot of planets with highly, developed, technologically capable life, because we know on Earth it took a very, very long time for that process, to play out. But we really don't know. I mean, the people who say that they believe in a lot of intelligent life or they don't, we don't really know. We just don't know. So it could go either way. But we just don't know. I would bet the number in the Drake equation, the n, is a very small number. But I could be totally wrong, and I hope I'm wrong. And I hope you don't think I'm crazy. Let's see, there's a question back here. Yes?
My first question would be, do those amateur astronomers use adaptive optics, or are they doing their discoveries without it?
They are, as far as I know, I could be wrong on at least a few individuals, there's no adaptive optics, because it's basically you're just measuring the light. Like, you don't have to improve the resolution so much. Here's the thing, if you have a night with really horrible seeing, your data for that night's not going to be any good. But as far as I know, this is not being used with anything more than, just good telescopes and CCD cameras. And I don't think they're using adaptive optics. At least most of them are not.
The comment I was going to make is, it only takes one advanced civilization, maybe 1,000 or 2,000 years, was advanced back then, to do it through the galaxy and populate the planets.
Right, and that's kind of a variation of the what's called the Fermi paradox. Like, where are they? If there's other civilizations, once they get, significantly more advanced than where we are, they should be able to, either they or their machines, to basically, colonize the galaxy. I mean, there's calculations that show that this could be done in a few million years. Despite the long travel times between stars, a sufficiently advanced civilization could do this fairly quickly relative to the life of the galaxy.
But they're also following the prime directive.
That's right, that could be. I mean, it's certainly possible. I personally, I've read about UFO stuff. I personally don't find the evidence very compelling, although I know other people would disagree with that. I don't completely rule out the possibility that there are other civilizations out there who are aware of our existence and monitoring us. There's no evidence in favor of that, but the Star Trek Prime Directive might hold true here. If they knew about us, and let's say they're very mature, they've stopped fighting wars, they have incredibly advanced knowledge and technology, do you think that they would want to contact us at this point in our existence? I think they probably would not, that they would be more interested in just watching us see how our civilization evolves without any interference. So, I don't completely I don't give it a high probability, but I do not completely exclude that possibility.
We're already here.
Yeah. Yep. So here's the thing: if there's other alien civilizations, NASA was hoping to build a mission that would launch like in the next 10 years or so, called Terrestrial Planet Finder. That if NASA is given the money by Congress to build this mission, we can start measuring the atmospheric composition of Earth-sized planets orbiting in the habitable zone of planets within a few dozen light years of Earth. So let's say we find an Earth-sized planet orbiting a solar-type star in the habitable zone, and you find, let's say, methane, free oxygen, and water vapor in the atmosphere. That would be maybe not proof, but very extremely powerful evidence that that planet has some form of life on it. Now, Earth has had that signature for hundreds of millions or even billions of years. An alien civilization that would take a spectrum of Earth over the last hundreds of millions or even billions of years would have identified Earth as a life-bearing planet. So the argument is, would you just let Earth drift by, or would you send something here to investigate a planet that you have very high confidence has life and learn about life on another planet? Zuckerman, in his counter to Seth's article, argues that intelligent civilization is going to want to do that. So it's certainly true that if there are a lot of other civilizations, somebody's been aware that Earth is a life-bearing planet. If technologically civilizations are common, because the ability to launch such a space telescope is really right now within our reach. Like, we have the technology, we could do this. It's a matter of funding. And if we can do this, then certainly civilizations more advanced than ours absolutely could do this or could have done it in the past.
Sarah Palin said she saw another civilization from her house.
Oh, this is okay, yeah. Let's see. She must have a good space telescope, right? Let's see. Any others, or do we want to get to the raffle? Yep.
I was wondering if the amateurs who are searching for planets that are transiting stars, exoplanets, do they look at stars that have already been identified? How do they pick stars?
That's a very good question. Most of the stars they look at are stars that we know have a planet from the radial velocity, because then you can, we know there's a planet there, and you can also, from the radial velocity plot, you can calculate to within about a 24-hour time period when the planet, and that's what Greg Laughlin does at UC Santa Cruz. He calculates when the planet should transit if it's in the line of sight. And then what you do is you align astronomers around the world at different longitudes. So because you don't know about weather, we don't know exactly when the transit's going to take place. You can just kind of get a window. So then you get a network of amateurs. So as Earth rotates, if you have enough people doing that observation, it's almost guaranteed you're going to see the transit. If you miss it, then you have to wait. But if let's say it's a 5-day period planet, you only have to wait 5 days for the next one. But if let's say it's a planet with like a 200-day period, then you have to wait 200 days for your next opportunity. Now, obviously, too, the closer the planet is to the star, the higher the probability is that it will be in our line of sight. So, the real jackpot would be to find like a transiting planet with like a 100-day or a 300-day orbital period. Certainly Kepler has done that, but for amateurs, they're concentrating on a little bit lower, things from like a hot Jupiter with a 3 or 4 day period out to maybe like 50 to 100-day orbital period. But they're going to find more because, you know, they're doing it. There's enough planets known that you do it enough times. It's like the Russian roulette analogy. You do it enough times, you're going to eventually, you know, it's not a matter of luck. It's a matter of statistics. Let's see. Yeah, right here.
I teach high school science, and so what I want to know is, of this, what do you recommend we could do to get the students doing something? I mean, we obviously can't just run out by a telescope, but what could we do that'd be, like, is the Planet Hunters website the thing?
Planet Hunters would be perfect. In fact, Meg Schwam said a lot of the citizen scientists doing Planet Hunters are like school age. That would be perfect because all the kids need is a computer and an internet connection, and it's something that that you can do, you know, within like an hour of going onto their website. You can be up and running doing the work. So it's something that's very easy to do. So that I would say they start off with that, and if you have some students who are really ambitious and really, you know, on their toes, you know, and maybe their parents have the money to buy them equipment, they can later get into looking for the transits. But that's like a whole different level of technical detail. But certainly, you know, there's, you know, some of the student projects that win, you know, like a science awards from these, you know, big corporations. You know, they're doing work of this caliber. So it's not completely out of the realm of possibility that like a really motivated and talented high school student could do the photometry work, especially for the transits.
So you'd recommend the transits as opposed to some of the other things?
Right. Yeah, I think
technical.
Yeah, exactly. Like the micro lensing is harder. So I would start off with Planet Hunters. The next step would be the transits, then the micro lensing. Now, doing the radial velocity, there's only a handful of amateurs right now that are attempting to do that. So I would put that as the lowest priority. But there definitely seems to be like a line of progression. Let's see, I saw back here.
That previous question was a great lead-in for mine. Then I wanted to ask you if you knew anything about the techniques that amateurs are using to do the radial velocity measurements. Because as I recall, the early discoveries by Mayor and Kales and Marcy and Butler, they used things like hydrogen fluoride cells,
right,
to get the comparison lines.
Right.
Are amateurs doing anything really special?
Not really, no. And I've actually talked to one of. Let me see if I can go back here, right here. Well, actually, I guess we can't see it with the lights on. But these off-the-shelf spectrographs, like the ones made by Cheliac Instruments, that's a French company. So I've actually, in fact, I saw him at NEAF this year, is Olivier Tizzy, T-H-I-Z-Y. He's one of the owners of Cheliac Instruments. Now, Cheliac Instruments, this is interesting. This is a company developed by French amateur astronomers. And they're like, we want to do spectroscopic research. At the time, there weren't really commercially available spectrographs for amateurs. So they go, well, we'll build one. So they've now turned their invention into a company. And using just their own home-built spectrograph that they built themselves, shown in this picture, they have detected some of these radial velocity planets. And it's because they produce fairly strong signals. These are massive planets, you know, the hot Jupiters. My guess is because they don't have that more advanced equipment, a lot of the radial velocity planets that are further out, they wouldn't be able to, you know, they're only going to get the low-hanging fruit with their relatively crude equipment. But it's still, I mean, this is still a very good spectrograph. I mean, good enough to detect a transiting or a radial velocity exoplanet. Let's see, maybe I'll take one more because I know people want to get to the raffle. Let's see over here.
I just have a comment.
Yeah.
We'll probably never be found by an alien people if the jerks that run their country fund us like our
Yeah, that's right. Yeah, I mean, I want to make it very clear. The only barrier to building terrestrial planet finder This was a program that was receiving funding a few years ago, and the technology was being developed. There was actually going to be a precursor mission called the Space Interferometry Mission. This technology was being developed. It's basically taking the interferometry technology that we already use, for example, at the VLA in New Mexico, but also like the Chara array at Mount Wilson, which is using optical and infrared. You adapt that for space, so you don't have to look through Earth's atmosphere. This is difficult technology to do it in space, but and I've talked to a number of astronomers about this. There is no at least foreseeable technological hurdles that say we can't do this. You just need to give the scientists and engineers the resources to do the technology development and the testing. I mean, I have no doubt that this is something that if Congress, our government changed its mind and decided to make this a priority, we could definitely launch terrestrial planet finder like in at least 10 or 15 years from now, and within probably a few years of its launch, we'd be getting spectra of Earth-sized planets orbiting nearby stars. The only limit here is not the science or the technology. The limit is the funding. This is a mission that would probably cost, probably on the order of about $5 billion. On the order of like Hubble, the Cassini mission to Saturn, or the James Webb Space Telescope. This is not like a $50 billion mission or like a $100 billion human mission to Mars. This is a mission that's basically within the same price range of some of missions that we've already flown out of NASA. So I personally think, and I actually wrote an editorial a few years ago in S&T, I would like to see NASA make this a priority, that one of the missions for NASA, for mainly its unmanned program, both solar system exploration and space-based astronomy, is to make the detection of life on another planet a major scientific goal of NASA, to help focus future missions to be designed to focus in on that question, because I think that's it's a burning scientific question of deep interest to scientists, but B, I think this is a mission that the public can rally around and support, because probably every one of you in the audience is curious how much life is out there. Raise your hand if you're not interested in that question. This is a great question, because it's of interest to the public and the scientific community, and certainly the first discovery of life on another planet, whether it's on Mars or in the around an exoplanet by studying its atmosphere, is going to be a watershed event in human history. And it's frustrating for me because I don't think the finish line is that far away, where we're getting to the point where this can really happen within the lifetime of everybody in this room, and it's a matter of committing the resources to make it happen. We're not limited by the vision of scientists or the ability of our engineers. So I probably should stop here, and so we can do the I guess there's going to be a short little break, and then am I correct on that, Roy?
Yeah, just give us time to get set up.
Okay, we'll just get set up, and then we'll do the raffle. Thank you all very much.